Hi there, I'm Chris, and I work on code navigation and intelligence tools at SourceGraph, and today I'm going to be talking about LSIF and Go. First of all, what exactly is LSIF? Well, LSIF stands for the Language Server Index Format. It was originally developed by Microsoft, and it defines a format for saving code intelligence information to a file. That means it decouples the complex language analysis from whatever UI you're using to view that code. The UI can service interactions such as hover documentation, jump to definition, and find references without needing to have a language server running. This is similar in spirit to LSP, which you might have heard of. It's the protocol that GoPlease uses to communicate with editors. So you probably use it on a day-to-day basis. You won't directly interact with LSIF, but some of the tools you interact with might use it. So when is LSIF useful? It's pretty useful when you're browsing code remotely. That's when you don't have the source code on your computer and the remote server needs to provide code intelligence. This might be on pull requests, when you're viewing code on SourceGraph, GitHub, GitLab, Bitbucket, anywhere else. There are already many ways to provide code intelligence, each with their own trade-offs, so I'm going to describe a couple here. But let's consider speed, for example, how long it takes to jump to definition, and precision, which means completeness of results, accuracy, and correctness. SourceGraph runs some language servers remotely, and they've proven to be very precise, but not always fast, especially upon the first interaction on the page. After indexing, ctags is very fast, but it's not very precise. It doesn't index local variables, and it's difficult to get type information. LSIF is another point in the design space. It's a bit early to say definitively, but LSIF will probably be faster than language servers because the language analysis is pre-computed. And it's probably going to be more precise in ctags because it includes local variables and it is generated with type information present. So I want to go through a running example of how do you actually generate LSIF data and how does this work internally. So let's start with this running example. First, what you do is walk the abstract syntax tree, looking for identifiers like function names, variables, and constants, and keep track of whether or not each one was a definition or a reference, along with their locations. Then you link the references to their definitions. There's some Go packages that can help with this. There's Go AST, there's also the Go packages package. And now that you have all these definitions and references, you have vertices and edges that can be assembled into a graph. And that represents all the information necessary to provide code intelligence. The primary reason for representing this as a graph is just for compactness. And it turns out these graphs are rather large. And finally, that graph is then serialized to a file in new line separated JSON format. Each vertex and edge is a separate line, as you can see here. You'll actually see as well the text document hover and text document definition calls from LSP. My teammate Joe built a command line tool for generating LSIF data for Go. It operates in a similar fashion, walking ASTs, keeping track of functions and variables, and writing new line separated JSON to a file. Here's the output while analyzing project. As it stands, LSIF poses some significant challenges. These graphs are enormous, and when serialized to disk, they're multiple orders of magnitude larger than the original source code. Some ideas for reducing or mitigating that include storing the graph in a specialized database, maybe SQL, maybe a graph database, compression, filtering out uninteresting code intelligence information, and doing incremental updates, so commit over commit. You don't want to recompute the world. You just want to recompute the files that changed. Only a few languages are supported right now, TypeScript, Java, and Go. LSIF Go takes minutes to build and serialize the graph, even for medium-sized repositories, so we'll be looking into optimizing the logic inside of LSIF Go to make that faster. Currently, the LSIF data needs to be regenerated for each commit, but it might be feasible to store just the deltas from commit to commit to avoid recomputation and reduce disk usage. Also, cross-repository support will probably require some kind of deterministic naming scheme for all exported identifiers in Go packages. The main repository is Microsoft LSIF node. and the spec is up there as well, and SourceGraph will be blogging about our experience with LSIF in the near future. Thanks for your time.